So my name is Christoph Scher. I'm from ETH Zurich in Institute for Atmospheric and Climate Science, and I will be chairing the last session. And this will start with a presentation from Stefan Nnimann. Stefan Nnimann has an interesting career behind him, also in front of him, of course. So he did much of his education in Bern, but then spent considerable time in the United States. When he returned to Switzerland, he was on a six-year position at ETH Zurich as a SNF professor, and now he's chair at for geography at the University of Bern, where he does a lot of very interesting research. His main research is focusing on the reconstruction of weather and climate during the past 400 years. He has really done some wonderful work about past climate variations, influence of volcanoes, and so on. For instance, he has out two really interesting books, one about climate variability and one about 1816, the year without summer. And so Stefan was also a lead author in the working group 1 of the 5th assessment report of IPCC. Today, he will be talking about characterizing the current climate. No room for surprises.
So thank you very much for the introduction, Christoph. Thank you to the organizers, not just for inviting me, which is of course a pleasure for me, but also for organizing this very special event and organizing this not just once, but for the 19th time. I have attended many of the Swiss Global Change Days. This is always a fixed entry in my scientific agenda, and so I'm really glad that this event takes place. Thank you very much for having done that for the last 18 years. I hope you have enjoyed today's program and also today's weather outside, looking at the bright clusters. And I'm sure that you want to enjoy the evening as well. So I try to be short, and I ask Christoph to be a very strict chairman and stopping me from being too long. Now, I will not go back to 1816 in this talk. I will speak about current climate. And maybe I want to take a step back a little bit. We have heard a lot about climate and climate change, but we should also at some point ask the question, how well do we actually know climate? And not just climate change, but just mean climate. And so in my talk, I will speak about climate change, but I also want to just give a few words on how well we can do that and how we do that and what the implications are. So this will be an overview talk, and I hope it's not at a too light level. And I would like to start with showing climate change. This is climate change as depicted in the 5th assessment report of the IPCC, and obviously this is a model result. We see the change in average surface temperature from a present period to the future period. We have no future observations. This must be model simulations. But it implies something. To the reader, this implies something. We can add this change to something like the real present climate. Not the model present climate, but the real present climate. And so the question is, do we know the real present climate? And of course, we do have some data, but this is also to a large extent a black box, at least to many people. So this is an example, one of many I could have shown. It shows the annual mean temperature of the Berkeley Earth Surface Temperature Initiative. This is a map of temperature on the globe, and I would like to go a little bit beyond that and see what is behind it and how good are these estimates. But also, there's another aspect that we have heard in the previous talk on the adaptation deficit. I mean, knowing the present climate is also important for asking the question whether or not we are really adapted to current climate, and I think this is not just for developing countries, but this might even be the case for Switzerland. And then of course the next question after this one is, do we even know the relevant return periods for such event, be it a hurricane or even winter storms in Switzerland? How frequent are events of the type of Berlin, for instance? Do we actually know that? And so I think there's still a value in looking just at current climate. So the questions I want to ask is how well can we characterize current climate and also changes of climate over the instrumental period, where instrumental period can be satellite period, it can be also 150 years of surface temperature series. And then one special focus, we have heard about climate services, and one prominent product of climate services are, or will be, at least from Copernicus, reanalysis. And we are working on that, so that's also one of our research topics. So one question always will be, and what about reanalysis? Can they do that, and how good are they? So how do we characterize current climate? Of course we have observations, and therefore I guess Stuart Lane would say this is easy science, and it is to some extent. It's easier than sediments, but nevertheless there are some pitfalls and some difficulties we have to master. We do have observation networks, we have surface station, we have remote sensing. Actually, it's incredible at the moment what we have in space, and this will of course change the whole talk. If I would give this talk in 20 years, it would be totally different. And you have also some other sorts of platforms, like the weather balloons. But specifically, if we work with surface data, we have to do a lot of work to come to a product that looks like the one that I have shown you just 2 slides ago. Now, I want to bring in the historical dimension a little bit just by showing you how the observations have developed over time. This is a semi-quantitative, semi-sketchy figure on the observation system development over time with a log scale of the number of observations going back to the 19th century, where nation states have formed and developed weather services that were powerful enough to sustain operations over a longer period. So we have networks that provide us with surface data. At some point in the 1930s, 40s or 50s, it was realized that upper air data are important, and weather balloon observations have started, but then really the game changer obviously are the satellites. Satellite age started in the 1960s for weather and climate application, but really actually what changed it was the year 1978 or 1979, where we had a launch of several satellites, and now just in the last few years we have really new generations out there that helped us tremendously. I'm not an expert in ocean, but I would like to mention also the Argo flows. That is really also a revolutionary kind of change of the observing system in the ocean. I will not speak about the ocean for the rest of the talk, just as a reminder. Similar changes are going on in the ocean observing system. So if we now look at the different sort of data sets that we have, I try to put them here in a cube that shows time on the x-axis and space on the one horizontal axis, and some sort of complexity in the vertical axis. We have the in situ observations, so the ground weather stations. They go back far in time, at least some of them. They never will cover the full space. By far not, and of course if we go back in time they shrink in amount dramatically. Then we have all sorts of remote sensing instruments. Now I showed them here as space filling, which they are not actually, but much more at least than in situ observations. Then increasing level of complexity. They are more complex in many ways, as deriving climatologically relevant variables from satellite data is always an ill-posed problem. You have to use retrieval algorithms, radiation models, etc. Then we blend these data with other products, gets even more complex, and the most complex of all are the reanalysis that then use a full-fledged weather prediction model to come up with an estimate of the atmospheric state. They are the most complex ones. Now just one word about reanalysis, because it's important to me, and I guess it's important also to the community. This is just a selection of the data sets that are out there at the moment, and I just would like to highlight a few of them. These down here, the 320CR, ERA20C, SERA20C, are surface-based reanalysis. They use just surface pressure, and these two in addition, a little bit of marine wind. They don't use any temperature information in their simulation procedure. They do use sea surface temperature to force the model. And the other one I would like to highlight is this one here. This is the newest kid on the block. It's ERA 5, and it is a product, or will be a product of Copernicus Climate Change Services. Will eventually go back to 1950. At the moment, what you can download goes back to 2010, I think. I'll show you some slides later on. Now, we have heard from Jörg Pfister in the morning that there's big science, and science is no longer the undertaking of just a few, but of many. This is the example of the analysis data set, fits that very well. They are hugely successful, and they are hugely used. Now, I wrote here approaching 50,000 citations. I made up that number, I must admit, but it is approaching. Don't quote me on that, but I did the calculation about a year ago, and it was something like 45,000, so it must be 50,000 by now. And now, if all of these citations do relevant, insightful scientific work, this means that a lot of what we know about the atmosphere is from these data sets. So I think we should take a look at the data set and see how good they are. So let's start, and let's start with temperature, which seems easy. Now these are two maps. The Berkeley one I have already shown, and I just show you one other map from the University of Delaware, just showing annual mean temperature over land. Now there's the notion around, and this is actually to some extent true, that it's very difficult to measure the absolute value of global mean temperature, and this is somehow reflected here. If we average now over the globe, we get a number of 9.17 degrees and 8.77 degrees here. 0.4 degree difference, that's quite a bit, and we could say, okay, that's really a large uncertainty. But we have to be aware that, first of all, we see here an infilled product that is based in the last few decades maybe on 20 to 30,000 stations based on the data set that we use. If you go back in time, it's just a few thousand. But then we interpolate and extrapolate quite a bit, and this, of course, over Antarctica, for instance, you can imagine in 1951, there's actually nothing around. So this is extrapolated also in the interior of Africa. Even now, we lack observations. But some of that is not really a real difference in terms of mean temperature, but you can also see, or maybe you can't, but there's a different resolution, for instance. And what matters also here in that map is the topography and how it is resolved in such a data set. That's one. The land sea mass, you can see that the Indonesian archipelago here is very different than here. This has much more land. Shelf ice, for instance, is another one, etc., etc. So some of these issues are real issues, but many of these are kind of academic issues. It's also a matter of definition. How do you define actual temperature? And if we express temperature as an anomaly from that, the differences vanish to a factor of 10 or so. What you see here is the development of global mean temperature from 1970, and we see 6 different products from 1970 all to 2017. So first of all, you see that the different products, I will come later to what has been done here, they differ to some extent in some periods, but overall the difference, even if it's large, it's at most 0.1 degrees Celsius and not 0.4 degrees Celsius. So I like to look at this figure because I was born in 1970, so this is the change of temperature during a lifetime, and I still feel young, you know. And this is 1 degree Celsius of change. So we have heard that during our lifetime, science has produced half of the knowledge of the Earth in just one lifetime, but also in my lifetime, half of the 2 degrees are already spent. I think this is important to look at. By the way, here is where ProClim was founded, so early on, and since then we still had some increase of 0.6 degrees Celsius. This is when the first Swiss Global Change Day took place, and we still have an increase since that time of 0.4, 0.5 degrees Celsius. We should keep that in mind, actually. So I said that some of the things are systematic, they average out, or they are due to the definition or so. But not everything. Of course, you have real problems and real changes in the instrumentation or in the observing system that we have to account for. For instance, change in the shelters, in the instrument shelters, they leave an imprint, and we have to correct for that on the marine side. This is how sea surface temperatures were measured until the 1940s or even later in some places. Nowadays we don't use that anymore, so we have to correct for that. Or changes in location. Typically what happened in the 50s, 60s or so is that the stations were moved to the airports, and we have to account for that as well. And of course, you could do that in different ways. There are assumptions behind doing that this way, and so you need to correct, and this can be quite significant. So this figure here, I just first would like to focus on the lower one. This is the American product from NCDC, which is now called NCI, that shows if you do not do it, that this is global mean temperature, land and ocean, and this shows if you do no such corrections at all, and this black line shows what happens if you do the corrections. So in the recent time period there's not much that changes, but in the early time periods it's quite significant, so you have to do corrections of that sort. And now of course the question is this relevant nowadays? What are the quality issues here? And figures of that sort, we heard today about the source-based legitimacy from Geraldine, and I think the figures of that sort play an important role in that process, but there's also the delegitimization that happened in, when was it, 2008 or so, ClimateGate. This had an effect actually on the way we, so this was of course a very unfortunate thing to happen, but for the observing community it did have some impacts on how we look at errors, and I think we have really learned much more about the errors and the quality issues in the data set. It has led to corrections of the data set, but these are relatively minor. This was a science paper then that concluded that actually the increase that seems to have slowed down for some period from 2000 onwards to 2012, 13, actually part of that was due to inadequate corrections. So are there surprises left? I think this could be a surprise, I'm not sure. If you look at this period in the early 20th century, if you look at the spatial pattern of that, a lot of that is in the Southern Ocean and South Atlantic. It looks like a spatially consistent pattern, so it could be very interesting, but early 20th century data coverage in the Southern Ocean, I wouldn't bet my house on the quality of that data. So this is where, for me, the most important surprises could be. Now, I want to say a few words about reanalysis as well. Typically, when we look at reanalysis, it's not global mean temperature that we look at. We are typically interested in much more fine-grained view of the climate system. But we can do it, and this is interesting for those products that do not use temperature. So in that sense, you have independent information, like 20th century analysis uses just pressure. It does use sea surface temperature as a model boundary, so in that respect, it's not fully independent. But if we just look at temperature over land, it's still an interesting comparison, and the black and red lines show the observations, and the blue is what this reanalysis does, and it does quite a good job, considering that we just assimilate pressure information. The last 40 years are actually relatively well done, and then if you go back earlier, it starts to be a bit more problematic. We have model biases. The model feels different than the real climate. And if you do not have a lot of information, then the model would like to stay in its comfort zone and to constantly push it out of its comfort zone, and this can give us things of that sort. So, surface temperature, how well can we characterize it? We have an increased understanding of uncertainties. Gaps are, of course, inevitable. I haven't even talked about temperature over ice, huge issue, Arctic sea ice, etc. So, but the uncertainties are increasingly well understood. Already, okay. We have a good agreement since the 1950s. and also in the reanalysis. Now, this is not the case everywhere, and if I had more time, I would dwell more on this slide that shows 100 hectopascal. Temperature at very high altitude, an important altitude in terms of processes of climate forcing. And here, so I don't go into the details, but here we still have quite some discrepancy, 0.2 degrees difference prior to 2007. From then on, we have a very good agreement. Now, here we have some radio occultation satellites that give us very important information. So, no more details, just to make the point, at 100 hectopascal, there are still surprises. But since we have so many satellites up there, 2007 onward, even that is relatively in a narrow bandwidth. Precipitation. Also here at first sight, comparison between station-based precipitation fields, mean precipitation over this 30-year period, two products here, a satellite-based product and the reanalysis. At first sight, this looks great actually. Differences seem to be small, at least when you look at the entire scale. They seem to do a good job, but we already see here, for instance, over Africa are some differences. If we look at the continental scale, we do see differences. So this is continental mean precip over continents, and the same products plus a few more, including era 5, for continental scale precipitation. And we can see, and this I find quite fascinating, that almost all of the differences are systematic. So we have too much precip over North America here in that data set, and well, too much, a lot, and much less in that data set. But the changes are in extremely good agreement. Maybe with one exception, Africa. And so this is the data set I have been showing before, and so here really we have an imprint of the increased satellite data that do a good job. Okay, even worse on the local scale, I skipped that. And I also skipped that. Extremes. Now, how well do the analysis do with extremes? Here you see the difference between 3 reanalysis and the fourth one being era interim, in terms of the return period of the hottest day per year or the wettest day per year. So this should be a 1-year event, so if it's white, this means that this shows the same thing. Actually, they will be biased. But so white is good and the other colors are not good. And what we can see is, if you look at the mid-latitudes where we live, everything looks white, so the analysis do a really good job, even for the extremes. But if we have the talk in mind from the morning session on where it really matters, where we have the impact from the multi-sector impact in terms of the sustainable development goals, it looks less well, because this is this region here where we really have still difficulties in representing extremes. So even if it looks very well for Switzerland, other regions are less well off. Okay, so one last word I would like to say on climate measurements and society, since today it's very much of a social sciences audience here, I hope, or I understand, and so maybe I can talk to you about that. There is a reason why we have a meteo station at a specific site like this one, for instance, and I think we should know why people measure climate at all in the first place. So just one example, that's a data map, that's a coverage map. What it shows is coverage of climate data in the year 1947. So you see sea surface temperature, the number of observations in the grid cell in that year, the stations that measure air pressure, and the weather balloons as well. Now, I'm also a geographer, I'm used to looking at maps, and I could ask a student in an exam, for instance, what do you see on that map? And the student in our department could be from the social sciences, part of it, and could answer very differently and say, well, I see world trade here. I see nation states, boundaries, I see boundaries. I see colonialism here in that map. And they are right. This is what we see in that map. And if we then come from this map and produce a smooth, nice, neat daily field or monthly field, we lose that information. And I think this information is not just important because the the colonialism maybe still is in our data products, but we're no longer aware of it. But also, we have heard that climate services need the information on the user interface. They need to have information on climate society interaction, and this is what this gives us directly. It gives us directly information of why societies measured, why they obviously found it useful to measure, and why not, and why we have the structure as it looks like. So I just, as a final remark, would like to make the point that climate data are always societal products. Of course, the data people, they find this a nuisance. They want to get rid of all these biases and to make the best estimate they can from this data. But there's information here that is also useful for climate services. With that, I close.
Thanks a lot, Stefan. A really nice talk. I liked this last slide. I'm glad you took the time to show it. Questions? Well, maybe I can start with a question. You showed that just actually using pressure data, you were able to recover with reasonable accuracy temperature trend and variations. How do you interpret this result?
Well, I must say the sea surface temperatures at the scale of annual means plays a large role. But even if you would go to daily scale, it would look even much, much better. And so the assimilation system, of course, it knows where the high pressure system and the low pressure system sits, and it will direct the temperature, hopefully at the right moment to the right station. And this works really surprisingly well.
But actually the SSTs are in the product as well.
Yes.
Yes, so that must make a decisive difference.
For the annual mean, this must make a decisive difference, yes.
Okay, other questions? Please, Thomas.
I think we were all intrigued by the title of your presentation, but there were not very many surprises. You haven't talked, for example, about the ocean or about the cryosphere.
Yes.
Maybe that's an opportunity.
That's an opportunity. Actually, I wanted to have the conclusions that we are pretty sure that we have not too many surprises left. We had already a surprise over lunchtime, and so I think that's fair enough to leave it with that. But you're right. So I cannot say something about the ocean. I have no expertise on that. We are working in a project where we try to make a global daily temperature data set that blends satellite station and station data, and their temperature over ice is really a problem. It's very difficult. And so I'm not sure whether it's really a surprise. I don't expect a big difference, but at least challenges. So maybe not surprises, but challenges.
Okay, we have time for one or two more questions. Yes, please, Christoph.
Maybe one of the surprises for those who don't work with the reanalysis data as closely as you is this jump in the 2007, I think, around in era 5, right? And well, my assumption would be probably it's new satellite products that came in. And are there any attempts to, get rid of or at least characterize these effects when you get new data in, and because this is really, I would say, ugly, because it makes it hard to assess any trends from these data sets, right?
Yes. So we in ProClim 2, we have started to work on era 6. The hope is era 6. No, but you're right. This is satellite data, and the unfortunate thing, and we have to look into that, because these data, so era 5 actually doesn't unofficially go back that far, so that might even be redone actually. It does assimilate these sensors here, so therefore we have to look what happened, even whether they were kicked out of the simulation system or what happened. So this information was, at least part, was assimilated, and it didn't affect the model. But then when the number was too big, it made a jump, maybe because now it accepted the data, because some other satellites had the same. I don't know, we don't know.
We can take one more question. Maybe one would also ask you, show how the climate is changing. Do you expect that with the existing data that we have from the past, but using new methodologies, interpretations, and data assimilation system, will we have, until how many eras do we have to watch? When will the series from era 1 to 5, when will that converge?
Well, I think after 2007 we have it already now. If you go further back in time, then, well, with era 5 it's 1950. To get consistency, even for the tropopause level back to that time, is very difficult. I don't know how many era versions. So the focus of the era versions goes more into the ocean now. So era 6 will be coupled.
Okay. Yeah, one last question, please.
Yeah, how well can we predict extreme events in the future? So that go beyond the period of 150 years of measurements.
In the future, so you mean the statistics of extremes in the future? Yeah. Oh, there are so many experts in this room that could answer that question very well, but I cannot. So, but I guess we have so they can raise their hands and then you can approach them. They don't want to raise their hands. Approach him after the talk.
Another one is standing there.
I think, I think we wait for the next global change. Maybe then there will be the answer. Yeah. Okay, I think that was very interesting. Thank you again, Stefan.